Okay, so while we bring up the slide. So yes, I'll present we're gonna jointly present between Tomoko, Hiro, and me our work on slope disparity gating using a synchronized camera projector system. The authors are Tomoko Ueda, Hiroyuki Kubo, Surin, Takuya Funatomi, and Yasuhiro Mukugaiwa from NICE and Arizona State University. So what we're interested in is building active illumination systems for what we call selective imaging and masking. And the background of this is there's a lot of visual cameras in our daily lives doing tasks like surveillance and video conferences systems and so on. And these cameras are acquiring real-time images all the time, which can actually compromise private information or compromise confidential information. For example, as shown in the figure, you might not want to have your cameras pick up confidential information like PIN numbers, computer displays, or documents that can be compromised in the image. So these certain applications require what we call selective imaging and masking to optically not get images with the objects in it, but selectively choose what images you want to capture. And so to show how our system does this, we're going to show a real-time demonstration, and then we're going to describe our system. So here we have a regular projector camera system, and it's illuminating a white sheet of paper with a confidential document, and this is just regular capture mode. And now what we want to do is actually mask out the confidential document. So as you can see, we actually can see the document, and then when we place it into a certain region of the imaging space, it gets disappeared. However, if we use other objects, they are still visible in the scene. So this is an active illumination system that is only capturing photons from certain parts of the scene and not others. Maybe we'll show that again. So again, here's the confidential document, and when Hiro puts it on the table, it vanishes. But when other objects are above the table, geometrically, they're being captured. And I'd like to point out that this is all done in hardware, so there is no post-processing. This is a real-time feed coming from the cameras, and we are controlling it. And at the same time, we can also do the inverse, which is we can capture only the photons that are coming from the table and block the objects. So you see here that any objects that are not on the plane geometry of the table are not being captured, while the confidential document is being preserved. So to explain this system, I'm going to turn it over to Tomoki Ueda, who's going to describe the research of how this is working.
Okay, thank you, Soren. I'm Tomoki Ueda. I'm from Nara Institute of Science and Technology. Now, I will describe how the system works in our paper. As you just have seen, we developed a system that selectively captures areas in the scene. To do so, we leverage recent work in active illumination using synchronized projector-camera system. In general, selective imaging is difficult as we need to control which light paths are captured by the imaging devices. Recent work by Otsulo et al. Introduced disparity gating to capture vertical planes of light in the scene, and works in scattering media such as fog or smoke. As shown in the right video, Wan et al. Introduced the method of imaging an arbitrary 3D surface using programmed light curtains, and show application to autonomous vehicles. Our hardware systems for disparity gating is based on a configuration of the EpScan 3D system from Otsulo et al. In this system, a raster scanning laser projector illuminates a horizontal plane from top to bottom. At the same time, the rolling shutter of the camera exposes one lobe of the sensor at that time. Both projector and camera are vertically aligned and synchronized in their timing to intersect the illumination and capture. This is different from EpScan and epipolar imaging because the projector and the camera are vertically aligned So they capture direct light reflection via disparity plane triangulated in the scene. Our method generalizes conventional disparity gating by introducing more degree of freedom to define the selective imaging volume. The geometry of intersection between the illumination and the capture planes determine what objects are captured. Only objects in the present at the intersection are captured via reflected light. So, in this synchronous scanning, the illumination and the exposure intersect only on the plane. So, it is possible to image only on this plane. In our method, we propose changing the depth, tilt, and thickness of this imaging plane using hardware parameters. Now, I'll explain each control in detail. We can control the depth of this imaging plane by the synchronization delay between the camera and projector. As shown in the left figure, the camera starts scanning after a certain time has passed since the projector starts scanning. Then the imaging plane is formed at a specific depth. As shown in the right figure, the larger the delay, the closer the plane is. We can control the tilt or slope of the imaging plane using the velocity of the camera rolling shutter. If the scanning velocity of the projector and the camera are equal, the imaging plane is formed vertical. If the scanning velocity of the camera is slower than the scanning velocity of the projector, the plane is slanted as shown in the right figure. Finally, the exposure of the camera controls the thickness of the imaging plane. A higher exposure leads to a large cross-section of intersection due to multiple illumination during a single exposure. This forms our volume for selective imaging. Our imaging plane or volume can be mathematically formulated using geometry of rays, assuming pinhole camera and projector model. The resulting imaging plane is the intersection surface as these scanning rays sweep across the scene. We invite the reader to refer to the paper for the full derivation. With our imaging formulation, we can simulate different plane geometries for a set of hardware parameters. Note how the smaller delay leads to the further depth, and the higher scanning velocity leads to larger slopes, which we validate later in real experiments. From now on, all results we will show from our hardware prototype demonstrated earlier. In our first experiment, we utilize a test scene with target planes at different depths and slopes shown here. By changing the delay to larger values, we bring the imaging plane closer to the projector camera as shown in this video. Okay, play again. Notice how only one target is captured at a time. Similarly, changing the scanning velocity allows us to capture the slanted target independently. As shown in this figure, only one target is captured by each sloped imaging plane. Finally, increasing the exposure time allows more than one target to be acquired at a time. As shown in the video, by changing the exposure time to larger value, the imaging volume is expanding. As shown in the first demo, our method can realize real-time mask imaging applications. We can shoot only on the table or without the table. Our output can be used as input to further post-processing, such as imaging painting. Here, we show the result of an off-the-shelf method to fill in the missing objects. The output results shows that it works well as an input mask image. Okay. Another application for our method is real-time imaging through fog. Since we can control the imaging volume, we can choose to only capture the object area without integrating the scattering media. We construct a test scene in the lab that has sloped road. This makes it difficult for conventional disparity gating to capture the road in a single shot. When fog is added to the scene, regular visibility in the image is decreased. Our method of slope disparity gating preserves large portion of the scene with high visibility as shown in this video. For example, okay, play again. For example, setting the imaging area on the road surface, we can image the entire left turn symbol. By increasing the exposure, we can image more of the scene, such as both the sign and the car. Okay. Finally, we can see blood veins underneath the skin. Using our method, we can align the sloped plane to the arm, thus improving the visualization of the vein. Our work has some limitations, mostly inherited from the hardware itself. Since we use an off-the-shelf laser projector, we can only tilt the imaging plane in the YZ direction and not the XZ direction. This can be remedied by moving to a controllable projector, such as those used in light curtains. Also, we currently tune our hardware parameters to determine the imaging regions. However, we are actively working to develop automated methods to determine these parameters by using structured light and semantic scene understanding. I will summarize this presentation. In this study, we synchronized the laser projector and rolling shutter camera and control the imaging area by changing the synchronization parameters of scanning velocity, delay time, and exposure time. As a result, we were able to selectively acquire the reflected light of the scene based on the geometry. And we propose the 3 imaging applications. For future work, we are interested in using structured light and coded patterns to help determine optimal hardware parameters and two-path light transport. Thank you for listening.
Hi, very cool presentation and kudos for the demo. So I was just wondering, for this demo, what did you have? How did you select the? How do you actually select the plane which you want to avoid or image in this demo?
So for this demo, like we said, we're tuning the parameters. So once you set the camera, we control the pixel clock, the delay, and the exposure to set the plane geometry to be on the table. So we're kind of manually tuning the imaging volume to set to there. But then the system is raster scanning the projection and the rolling shutter of the camera. So it's automatically optically blocking the light rays that come from the travel. And to do the inverse, it's like you can do the rolling shutter exposure, or you can expose everything except that row. So it's kind of like the binary complement in the rolling shutter is how you do the masking.
Thanks.
For the so for the vein example, what exactly is going on? So are you actually gating to a depth that's below the skin surface?
Yes.
Like if you shift the gate slightly, can you see the top of the skin surface, and then you can? Oh.
Yes. So, now it's again, because we're not automatically tuning the parameters. The arm has to be in a position in the YZ plane.
Yeah.
But then we set the depth to be some millimeters below the surface, kind of by tuning, and so we're not capturing the photons that are directly reflected off the surface of the skin, but ones that penetrate a little deeper.
So as you sort of continuously tune it, you can see it going from being able to see the top surface of the skin to be able to see.
Yeah. But of course, you know, it can't get to like the stomach because at some point, signal noise ratio.
Yeah.
You know.
Is this just the red channel? Is this?
This is just monochrome.
Just
just the red channel.
Yeah,
sorry.
just see deeper. Yeah.
Does it go through clothes? Does it go through clothes? No, I don't believe it goes through clothes.
Any more questions? Okay, let's thank all the speakers in the session one last time.